Welcome everyone to Cloud Computing and Big Data. We have our second part of Lecture 3, Apache Spark for Cloud Applications now. So we talked in the first part of the lecture really about Spark and the basics. And I said earlier, a proper introduction to Spark will be probably a whole week of a workshop or of a tutorial done by consultants somewhere. But of course, here you get at least the idea roughly what you can do with Spark. And if you go out in the field in companies, why Spark is useful. Remember, it's maybe a very nice framework, but it also comes for a cost of memory. Spark lives from memory. That means your servers, your computers need to have lots of memory. And as we know, memory still is a very expensive factor in buying computing. Cores are getting cheaper and cheaper. Storage essentially gets cheaper, but still memory is quite expensive compared to the storage capacities. And if you have petabytes to digest, maybe as we have seen in the word count, all books of a library as a digital versions, just to have a couple of words checked, how often maybe things are sports or history or things like keywords actually noted can be actually amount to lots of processing. And with this, Spark can do it very easily, very quickly. But you have to pay the price in the cloud of course, swiping the credit card and pay $28 for an hour. And of course, there you see quickly how this all sums up. And this will be a key theme in the course. So always when we use a cloud, of course, there's a return of investment for the cloud provider. Luckily, our educational resources sometimes have been free, but you can also imagine why they maybe removed this from the educational sector. I'm just guessing. They just removed it actually directly after my course when I've used it 2020, which is also funny, from November on or so. Of course, today you can easily use it for Bitcoin mining. You can easily use it for a lot of good things. And you get already, let's say, a small portion cluster for free. You can do a lot of things if you keep it operating for 24 hours every day. So maybe these days people are very afraid that people use too much Bitcoin mining on these systems. That's why they probably have also removed that from this. But that's just my guess here. I never have talked to them directly. For next year, we probably want to inform them before and try to ask again to get hardy insight, maybe as a special, allowance or so, but it was just no time and actually unexpected that they removed this feature. My PhD and me, we spent 1 or 2 hours actually finding that out. We still tried a lot of times because we thought it's maybe our error, but no, it was basically in the cloud. Good, but so coming back to the real idea of Spark, I said already here in an in-class, nice question for what you would use also Apache Spark, maybe even on your own computer or as a team within a startup on small computers. It has a very strong library support. So this brings you not only the parallelization benefits and memory benefits I talked about in the first part of the session. Also think about that you cannot do scikit-learn, Octave, MATLAB, throw it to Spark, and it will be parallel. That's not working because you have to parallelize the algorithms for it as well. So that means the libraries need to be parallel aware. Otherwise, it will be still serial, and then you don't gain a lot of things from machine learning. Hence, all these different algorithms that you have here are, of course, then organized and actually optimized for using parallel computing. And with this, it's actually quite a very nice set because it's all open source. And you can all use it. And basically, it captures quite the essence of what you want to do with data, right? You have data like traditional databases, data warehousing and things like that, where, you have a very homogeneous structure, again, name, phone numbers, contacts. These are examples of these SQL data sets. Then streaming is a lot about events, right? Really ad hoc data analysis. Think about, they have the Twitter tweets that are sometimes now in some stadiums shown directly on the screens, which are filtered. You can have the Twitter streams directly analyzed by just the streaming library. Machine learning is a very strong library for open source. There are many closed algorithms in machine learning that are parallel. So it's one of my research areas. I can tell you it's also nice to have that online and open source. And of course, Graphx, there are many different applications. One we will also look at when we look more to Facebook, how that operates. It's of course very inhomogeneous data, quite the opposite, right, of a telephone book. So Facebook lives just from likes, connections, it's a graph. So essentially there are lots of graph applications which really have this kind of social network kind of flavor. Now, when you compare it to, let's say, many different other projects which are in the open source field, they all maybe you don't need to know them, but they're known for their, let's say, speciality, Storm in streaming, Impala in SQL, and Graph with Giraffe. Since Spark is like kind of optimizing this in a very smart core, you see that adding then all the different, let's say, kind of different libraries on top really gives you a lot of, let's say, performance increase instead of, having the old Hadoop. But we know, of course, this is also the memory benefit here. But of course, they also don't really have this memory optimization as good as Spark. And that's why they are both all basically here much more lower in performance. And this is, of course, a nice stat that you have now from an application perspective, not anymore to have to deal with all of this jungle of 1,000 open source tools, which are actually in one way or another all dealing with data. Here you kind of just use the PySpark and can nicely program in Python with Spark and uses different libraries. So it has also kind of a usability improving. Also, of course, the data sharing with it and the memory use. Still, I want to show you also then how to use it as a quick walkthrough through all the different, let's say, ideas, how you can use Spark in applications with these libraries. As I said, also, don't forget the data. Many of what I'm talking today or what was basically in the video was very much task oriented. Of course, we always have to think about, we also put the task there where the data is. So large repositories might be sitting there already having, SQL databases from MySQL, for example. And you can then dock with them indirectly by having a Hive, Apache Hive language-like integration into basically Spark SQL into this library. And then you see again an example when you would do it compared with Hadoop. As I said, it's always dump to file, read from the SQL database. With Spark SQL, you have here just a fraction of those because, of course, you keep many of these in memory again instead of always involving the SQL database. So this is just one example where actually the API is very rich. Of course, Spark SQL alone, all the features and all what you can do is something which would fill probably 2 or 3 days, right? So I just give you here an indicator. Indirectly, we will use it in some of the demonstrations I will show you. You see a little bit how that works here. You have, instead of a normal Spark context in Spark session, you would have a Hive context. That's a specific part of an Apache project that's not so relevant, but it's integrated essentially. And then you have your typical SQL. So that is a structured query language. Someone knows SQL? Have you done this? Okay, the majority knows it. Very good. So essentially then you know the game. You can very much vary the SQL string here. You can do joins and things like that. If the data is available, of course, it's not a problem. And here's an example where you then combine this directly with a map of having all the different names then shown. And Hive takes care of this context with basically connecting to the SQL database. And still you have the same way of wording and connecting that basically a nice programming in the Python environment together with all the other Sparks. And then of course from there, you can immediately process it now. Basically the data frame will be transported or indirectly transformed into this RDD we discussed and then distributed on the cluster. Again, if it's lots of names that you get back from the SQL query, this will be nicely buffered and then put basically, as you see here, nicely out in the cloud. And then the number of iterations for doing this, basically you kind of very nicely get high performance in Spark. This was a very quick example, but as I said, also there will be a demonstration that I do with UHD Insight. And there you see in one of the elements where we use Spark, we also use the data frames that actually coming out of these. And I think it's much more easier and simpler to show you that in the practical example than here. But you can see that the violations in these examples are basically then coming out of sort of database. And then you can work with this kind of tables while you essentially then here have the opportunity to involve lots of imports from PySpark SQL functions, types, and so on. So we have seen that then basically in practical lecture 3.1, which comes next Thursday, on Tuesday, where we then talk about basically some practical examples. The other idea how to use Spark would be basically as a streaming library. And streaming is a very big field today, mostly because if you remember this 1 petabyte per 20 seconds from the sensor, the square kilometer array for the basically search there, there was so much data where maybe all is not relevant. So there are sometimes questions today, do we really need to store everything? Or do we not look for certain events to be stored? This is something what you can do. So in a sense, let's say just for some star occasions, we are interested in that, right? So we would define it. And this is the so-called data stream. There's a continuous stream of data, and we would define it. Another good example is maybe if you're a startup and you have a Twitter, and you know, those that are on Twitter that know it's too much information, so no chance to digest this. But what you can do is, of course, to hook the Twitter API and basically then look all the tweets through, put them as text through, and maybe just, you know, instead of saying containing Spark, the name of your company or your product, right? So CPP Games, example, EVE Online or something. So they would immediately out of this Twitter API with Spark on the cluster then get very quickly all the tweets that are just basically mentioning them, so that they can maybe find sentiment analysis. It would be an idea to find out, you know, if the people say this or that about EVE Online. I never played it, but I mean, there's probably certainly some people have this or that ideas, and this could give the company quickly hints. Otherwise, you have a manual person that has to go through all the Twitter tweets and say, oh, here's someone saying something bad, right? So, and this is manually very long process, and just one good idea how you could use Spark. And again, the way how you do it is so brilliant. When you think about the API, it's really a couple of, you know, transformations of the data and then actions. And then you basically have here a filter where you just can define it. And with a couple of words, basically, you get a scalable solution. So no matter what comes in, how long the stream will be, how big data it will be, because basically Spark is able to scale out, it doesn't matter to you. That's completely true. Of course, we know we have to swipe the credit card. In other words, we have to have the computing power for it, right? So this is something that we can steer with saying we want to have 30 worker nodes or 50 worker nodes or 100 worker nodes. If I'm in a big company like CPP Games, for example, maybe. The other thing we didn't really talk about was this fault tolerance again in RDD. So essentially when you progress, let's say on this kind of every second the data, of course, there could be a crash sometimes. And the beauty in Spark, again, compared to many other frameworks that you program manually, it will just continue. It is fault tolerant. The RDD will be basically from the manager notified as not working, will be resubmitted on the same data so that you don't miss, for instance, a couple of tweets that were happening, right? So this is also a very nice idea of this framework. It's not only very performant in memory and so on, it has this mechanism of resubmission of error, where usually, you know, when everything would be executed, a manual, you know, worker or administrator's look was everything executed. Oh no, this one not, then I do it manually. Yeah, that was a time before Spark and Hadoop. People have actually done this. They looked on the logs, said, yeah, everything is executed perfect. Oh no, here was an error, and manually resubmit and find the data for this. You can imagine lots of work, right, from manual. And this can be now all very much automated, and it's really robust in a sense that even if you remove data from one of the cluster parts, because we have replication in this, basically through the Hadoop distributed file system, it's something we will talk about in lecture 5. The data is several times available. It will just make sure to send the data again to the cloud, but on a different cluster with having the data again. Of course, it means you have to have a replication. If there's no replication, there's nothing you can do. But this is an example of the fault tolerance mechanisms that is really inside this, which makes it really, really nice for many operations, because as we know from, you know, much experience, and I'm 16 years in the fields, these clusters always have some errors, failures, some node gets down, some CPUs get overheated, some network connection is down, a switch breaks. So you can go on and go on and go on. And basically, the daily operation of a large data center is just working with faults. And if you have then software on top that doesn't care about this, means of course a lot, right? So you don't have manual interaction. It will just, you know, resubmit the data where it's possible, and you can just concentrate on the hardware issues. Of course, you can do also the word count here, very similar with a stream, at also the same capability essentially. Of course, you have to wait, or basically you do an online streaming. That means only until there you actually know the word counts. You never know what's coming in the future, of course, but at least you can have and trigger and filter the current status of the count. And of course, have to update the current count then to the old count from the second before. So that would be just one example of having a live real-time display. If you think about the library and you want to know history and sports, how many books are about this, you basically can have a real live pointer with the streaming library always directly counting on the fly. So this would be another example. Yeah, then machine learning, we already talked about this in logistic regression. I gave you another example. Have you maybe used k-means in Anna's course already? K-means clustering or any form of unsupervised learning clustering? Not yet. No, okay. So essentially clustering is another element. If you remember my introduction in the beginning, where I said classification is in a way beautiful. We have the two classes and there was a new bullet, a new point, and we would put it in one or two classes. And we learn from the existing classes and we'll do a decision boundary and can now basically define this new point comes in that or this class. Unfortunately, the life is not always like this so easy. So we talk about this when it's about clustering problems where we don't have the identity of these classes yet. But there is something in the data that enables us to do so. And you see here, just with the eye, of course, these kind of are closer together than the others. So when you think about Euclidean distance, the ruler distance, there must be some connection to this and this, but you don't know this. The data is not having our nice label Y yet, right? So clustering enables us to find essentially such classes, basically by going through the data and using some form of similarity measure. And k-means algorithm is one of the most easiest algorithms and is also implemented in machine learning, lib together with regression algorithms and many other things, decision trees, and so on, and actually a random forest, which is then the next bigger system that you would use. And the way k-means works, it initializes somewhere basically a kind of from all the means, a dot. And by iteratively going this, and again, you see now the iteration is machine learning, is data mining. It doesn't know the answer analytically directly. It only goes iterative by iteratively through this. And how you would do this here, you see, it's just a two-liner essentially in kind of MLlib in Python. Of course, depending that the data is maybe correctly modeled around this. And you have to specify a little bit in k-means that makes it the k in front. How many clusters you're searching for? K is a parameter where you steer how many clusters. So here you have basically 4 clusters. So you would have basically 4 as a parameter that you think here would you of course put 2, right? To see that this maybe would be 2. And then it would be clustering automatically, basically those which have, let's say, the closest distance. And the end result would be then, you see in the coloring, those that have actually then come together. Of course, this is one of the most simplest you can find. One of my PhD students implemented the DB scan in parallel, which is much, much more tougher. It's a density-based one, and it's actually also dealing with lots of sorts of things where k-means cannot work. K-means has, unfortunately, the convex property, so it must be convex problems. And essentially, DB scan can also do all sorts of forms. That's not a problem except the bow tie. So you see, there are also advanced algorithms for clustering. That's what I'm getting to. But of course, you can also do that in parallel. And yeah, the way how you use it is you just, use the MLlib, you import basically k-means out of the ML library and beautifully can, directly work on the data. And no matter how big the data would be from all the points, it will scale out and actually can basically then work easily with your data set. And this is another very good example where we basically have then also some practical implementations of more from the MLlib, what I'm going to show you, of course. One example of that, which is of course also relating to the last lecture we had, but also to the one I show you on Tuesday, is then again the optimization in the process. Think a bit always that machine learning has some optimization inherent. That's what we basically want to learn. And the optimizer is often a way to learn to minimize the error as we had last time. So in this kind of case, no matter it's basically this condition fail or pass with a food inspection, or as we said, 0 and 1, essentially then for the deposit, meaning I will do a deposit or not. In the end, in order to come to this decision boundary, you need some form of error measure to see from the existing labels and then nail down the error. So what you see here is, of course, a plot of error that you then essentially take a derivative from, and then you basically have an ascent. And I think that's also what we discussed already in the last, because it's an ascent, but we want to minimize the error. We take the minus here. This fellow is a so-called learning rate that we can steer, which nothing means in which iteration we jump, let's say, far or not. And it's sometimes a problem because not always will the error surface look so nice. We call it basically a local or global minima. You can see in a large error function, which can be very tough, actually, when you visualize it. Sometimes you maybe get stuck in a local minima, while the minimum of error would be somewhere much more farther away, but you kind of stuck with your learning rate. You don't, iterate. And once you notice, okay, the error goes up again, you stop. But of course, this is bad because there's much better, let's say, error somewhere. And then you would basically continue and you can jump over these problems. As an example, with the learning rate, there are also more optimizers today with Adam and Nesterov momentums, where it also takes the velocity of your downwarding downhill basically into account. But this is something for Anna's course. I think she will talk about Adam, hopefully, and about Nesterov momentum and so on. But I'm sure she will talk about SGD. Maybe she had already, or yeah, because many machine learning algorithms until today, neural networks, deep learning networks, they still use SGD. Of course, also more advanced versions of it. But in the end, the key idea is the same, minimizing the error function that you define. Good, yeah, talked about this. Just a short other example for the iterations to learn. And of course, this kind of speed that we will see in this logistic regression in k-means clustering or logistic regression, they all benefit now that they sit on top of the basics, right? From the memory usage we discussed, from the RDD we discussed. So all of that is now taking advantage that no matter what the algorithm is, in the end, some, of course, is related to the algorithm implementation itself. So it's okay implemented, so to speak. But the majority is also coming from the fact, because it's the huge differences that you notice here measuring Hadoop against Spark, that they take advantage of the basis from Apache Spark. And you can even go ahead and create new machine learning algorithms reusing the basis, and it will work for you, right? So that's also one beauty aspect of it. It's open source. You can simply rely on this basis and maybe use one of the machine learning algorithms and implement it. Good, so having talked about this, I think you get the idea of the machine learning library now. Just as a hint, maybe also connecting it to Anna's course. There are different classification algorithms. You will have lots of Bayes school, which puts a probability framework on top of it. You have the logistic regression that we already had in the course, the random forests, which are basically grow 1,000 trees, because usually one decision tree is very prone to overfitting. So you only use that in practice. You grow 1,000 trees, and immediately comes your parallelization, right? So we do 1 million trees, but we do it in parallel, right? And then we take the best performance out of it. Then we added bagging, boosting, and then basically we have a very nice framework of making classification, which is not prone to overfitting. And regression is basically not so interesting. It's just maybe real valued and trends and so on. In machine learning, we consider this a little bit like, well, a very, very basic topic. More interesting is then, of course, support vector machines and, random forests, as I discussed. This decision trees I already talked about. Least squares is very popular for collaborative filtering. So we will talk about this also when we talk about data mining in lecture 11, where essentially Netflix, we will talk about these recommendations that you see for movies, for these elements is usually using approaches from alternating least squares and basic different algorithms like collaborative filtering, thinking about not what other users bought that I want to buy also. There it's more like what other users that are similar to me have bought, right? So it's much more complex. So you have to identify what as a personality, which is very similar to me, not actually just, having a couple of favorites, like they look the Western, I look the Western. So we both may be interested in the next Western coming. So, but these of course are details for the machine learning course. We will shed a little bit lights on it in the lecture 11, roughly, to understand the concept of it and how, of course, you can use it then with Spark and other algorithms. Clustering we discussed, we just scratched the surface. There's chi-means, chi-median, the DB-scan algorithm, which is very famous. Gaussian mixture models is already a more advanced model. And of course, lots of data mining technique, association rule mining, so shopping basket analysis, what are things basically brought together. The difference again here is here it's a bit personalized, so much more complex and harder, right? We identify the personality and the kind of overlaps in that and distances. And here we just look at the shopping basket, what things were brought together. But both will come in lecture 11, essentially then as demos, basically also. From the graph library, I want to just give you also an example. I think you can imagine compared to the table, things like social networks are very homogeneous, but here and there, of course, have some common friends or some common video everybody looks, so things like that. And it's very powerful. And one of the famous, graph algorithms is PageRank. You maybe know that from the ranking of web pages, where a site gets usually more popular when more links are basically there. It's a very traditional way to show the importance of PageRank. And now you want to scale that. The whole web is, of course, very complicated to do this. And you have different other usage scenarios and see what are the stupid pages, which, are not really popular, but try to, modify the search engines in some way. And one of these algorithms is PageRank, where you essentially think just about how many edges are looking all the basically neighbors and going out. And with this, you ship a signal through them. So we go to a one-on-one example now to understand a bit the algorithm, but this is something what you can now at scale do in Spark. Think about all that the time. You have lots of lists of, let's say, links which point to another one from the network. And you have, of course, with this, the sources and the rank. And let's do a simple example maybe of these formulas here that you get the understanding. So it's a step-by-step walkthrough. Again, you have an iterative approach in PageRank. So you need to have some convergence of basically the changes in this. And of course, in PageRank, you can imagine those where everybody is pointing to is important, but also the important pages pointing to. So the matter how your PageRank is also important. So not only very much smaller sites that point to you, but also what big sites point to you influence essentially the site. And this is an algorithm where you have maybe initialized, let's say 4 pages here with 1, you define a certain base, and then the contributions really depend on how basically famous this one page is. So when you do your own web page, and University of Iceland web page will actually point to you, it's much more better than you have 100 friends, which almost never basically have been maybe hits on the web page, because essentially the page rank would be very low. University of Iceland would be having a very, very high ranking. Of course, as an educational one where lots of students always look at and where many people point to. And then you essentially just take the rank, take basically the neighbors, the link outs. That's important. So you see here, we have 2 link outs. So my page rank is 1. I divide it by actually 2 and would give him 1 and give him 1, 0.5. And you can imagine already 3 show to this. So maybe this would be the winner of the game when you now do iteratively the same, right? So thinking about this, so we add 0.5 to the game, to both sides, and then we have to compute this to this contributions, which is essentially then thinking about this link out. Of course, I get it also from the left side and I get it from the bottom. So actually I have 3 contributions here that make me quite powerful because 3 pointing to me, and one of it was very a strong one. So basically I have here, then this what you add as contribution. And now iteratively, this is how they compute the kind of ranking of the pages from the popularity, and the next iteration will be the same. And now you can go on and go on. If you want to do the math, please do. Just for showing you that's another iterative algorithm that can benefit from a more network graph character and scaling out. So of course you can imagine we don't want to know that for 4, we want to have this maybe for millions of web pages. Here's an example of 322 million links as basically just a number, and how you basically scale with Spark when you have the number of iterations and how it converges then over the chains of iterations. And basically, this is what we mean with convergence. You need lots of iterations to really bring down the changes to a few in terms of the change of the popularity. And here with this, you have already a certainty that, the page ranks, which are the highest, you want to report first in the Google search engine. That is actually coming also from the founder of Google at that time, the algorithm. Anyway, so I think it's not just that I show you this just for showing essentially Spark benefits. Again, of course, think about the number of machines matter. So I said about the workers, we increase them, right? You have to have the capability for it. If you have just one worker, you cannot maybe get an improvement in performance. But if you add, let's say, 30 workers, in other words, machines, or 60 workers, you break more the time. Of course, for Hadoop also, right? It's also part of the framework. It also can get the time down. But of course, this is, of course, multiplied with the memory usage, having more aggregated memory when you basically have more machines available. The downside, you know the game, you have to pay for 60 machines with high memory, right? If you have the money. At the end, just some examples in business applications. Yahoo using that for personalizing newspapers, web visitors on news pages. Basically, you can categorize news stories, as I already said, with sports or history, and then make them easily accessible on the right pages. Conviva is very famous for advertising, uses also different elements of actually Spark with the databases and so on. Use a lot of interactive capabilities. The details would need, a lecture each. So basically, I think you can go to the resources all the time. There are all the stories and the details, just to show you that Spark is really used in practice by big companies every day. And clear story and so on. These are all different, let's say, elements which are into interactive real-time product management where time matters, right? And with Spark, of course, you can achieve that. And of course, they have a business model that they maybe get reimbursed or through the customers all the price that they need for big memory machines, right? And this is something where, lots of elements are actually used differently. There's a large ecosystem I want to come to you. And basically in lecture 5, we will see how that materializes. It's not only Hadoop, there's Zookeeper, here's Hive, there's lots of databases we will see. So a huge ecosystem all works together and usually bound together in Hardy Insight, or you can also achieve that in the Colaboratory that we used. Now, this is an example where we also will come back to in lecture 6 and 7. You will use it in your assignment 1, and we talked already about it. So no point of maybe talking longer about this. Just I want to finish with a 2-minute video summary and maybe also a kind of pointer why so many different, let's say, elements are used in this and that really people using that in practice a lot. This is a video from Databricks. And again, I'm not paid by Databricks. This is a disclaimer here up front.
Hi, I'm Matej Zaharia. I'm a co-founder and chief technologist of Databricks, and I also started the Apache Spark project back in 2009 doing my PhD at UC Berkeley. Today, Apache Spark is the most actively developed open source project in big data and probably the most widely used as well. There are hundreds of people contributing to it every year, probably over 1,000 since the project first started, and it continues to rapidly add new features, new capabilities, such as libraries to do different types of analytics. What's unique about Spark at the highest level is that it's the only software framework that combines data and AI. So using Spark, you can do large-scale data transformations and analysis, and then you can immediately run state-of-the-art machine learning and AI algorithms on it. And that's super important for building AI products because AI is only as good as the data that you put into it. It's powered by the data. And so when you have a framework that can do both things and that designs them to work together, you can quickly build the highest quality application. So at Databricks, I personally focus on a variety of topics just around our technical and product strategy. So with respect to Apache Spark, I'm always talking to users, trying to figure out, what are the issues that they're having with it, what are additional features that they'd like to see, and helping to guide the contributions from Databricks in these areas of the open source project. In addition, at Databricks, we're interested in building a unified analytics platform that's end-to-end, that goes beyond the analytics analytics engine. So I'm also thinking all the time about the analytics process in general, how to enable enterprises and organizations to just reliably build data products as part of their business, and helping to design a lot of the key components of our platform that let our customers do that.
All right. One of the reasons why I wanted to show this was also the idea he nicely put, essentially this graphic, but also mentioned. When you do machine learning, you don't do it isolated. You would have data from different sources, click streams, video speech from your customers, interviews, you have customer data from usage. You would combine different sources. And then you have different algorithms directly nicely inherent, but you never know what the peak would be. So would there be lots of information, so you scale automatically underneath. The second thing he mentioned is a little bit at the end, this framework. So what we little bit left out here is the pipelining aspect in machine learning. I'm not sure, have some from you maybe took Hafstein's course as a short course about the data AI lifecycle? I don't know. So this is also a course where you learn a bit more. Of course, when you do it once, you want to do it many times. You operate the whole pipeline of data selection, data feature selection. You're transforming the data. You want to have this in a pipeline and execute again and again. Not just, using scikit-learn, import this and run the k-means and come back. Of course, you would have the load data automated, working on the data, preparing the data automated, the machine learning automated, and storing results automated in the pipeline. We talk about this in practical lecture 3.1 on Tuesday a little bit more, but of course would be also something which you maybe learn in Hafstein's course really completely over a couple of many lectures, because we can't do all of this here because it's basically a cloud course stimulated by usage for big data in machine learning. All right, so that's all I wanted to leave on the table for today. Some references, the good team, and yeah, thank you very much.